Hey everybody, this is the last section of chapter 6. Okay, so remember you don't have a math Excel for this, so hopefully you're plugging away at your exams. This chapter 6 is an exam number 3. You should be getting it on June 2nd. Okay, I'd like those in as soon as possible. I'm going to be posting videos and stuff all next week for chapter 7, so just keep working away. There's a lot of examples that kind of follow along with the notes. So do your best. Let me know if you have any questions. I'm happy to help. Okay, I'm on page 10 for the chapter 6 notes. Okay, so we're going to be dealing with population proportions instead of means. So we've been doing population mean, but now we're going to do a population proportion. And population proportion deals with, so the way we get this is from a binomial experiment, and the probability of success in a single trial is P. So we will be finding the point estimate for P as well as the confidence interval. Okay, so let's see here. So the point estimate for the population proportion would be called, it's called P hat. And the way we find it is by taking X and dividing it by N. And so this is called the sample proportion. Okay, where X is the number of successes in the sample, and N is the sample size. And then just remember that if you have P hat, you'll probably want to find Q hat as well, which is 1 minus P hat. And this is the point estimate for the population proportion of failures, or just Q. Okay, so in example number 1, in a survey of 1,000 US teens, 372 said that they own smartphones. We're going to find the point estimate for the population proportion of US teens who own smartphones. Okay, well, this is our sample size. This is the number that said that they do own smartphones, so that refers to the successes. So the point estimate is X over N, which is 372 over 1,000, or 0.372. Okay, so that's the point estimate for the number of students or number of teens who said that they own smartphones. Now, the confidence interval for a population proportion is P hat minus E, which is less than the population proportion, which is less than P hat plus E. Okay, and E in this case is going to be, we're always going to be using z-scores. We're going to be multiplying it by square root of P hat times Q hat over N. Okay. Now, the reason why we would be able to use a z-score is if we can approximate it normally, just like we did in the past in chapter 5, I want to say. So if N times P hat and N times Q hat is greater than or equal to 5, then we can approximate normally. Now, the mean for p hat is just the population proportion, and then the population standard deviation would be the square root of p times q over n. Okay, so let's go through the steps of finding the confidence interval for a population proportion so that we can try an example. Okay, so we're going to identify x and n. Okay, so x is the number of successes and n is the sample size. So then we want to find the point estimate p hat, which is just taking x and dividing it by m. Then you want to verify that the sampling distribution of p hat can be approximated by a normal distribution. And that's by doing n times p hat, make sure it's greater than or equal to 5, and n times q hat is greater than or equal to 5. Okay, because we need to make sure it's approximately normal so that we can use that z-score in the margin of error formula E. So then find z sub c that corresponds with C, which we've done the most popular ones. They should be listed on your tables right now. Then you're going to find the margin of error, which is E. And that's by doing critical value of Z times p hat, the square root of p hat, times q hat over n. And then last but not least, you do your confidence interval. Okay, so it's p hat minus E is less than P, which is less than p hat plus E. Okay, so now in this example, we are going to be constructing, we're going to be using what we had in example 1 to construct a 95% confidence interval. Okay, so I'm going to condense some of these steps a little bit. So for step 1, we're going to say that we already have that x is, what was it, 372, I think? Yeah, 372. And n was 1,000. So let's now find p hat, which we already found from example number 1, that was just x divided by n, so 0.372. Then I'm actually also going to find q hat. Which is 1 minus 0.372, or 0.628. Why is it so glitchy? There we go. Okay, 0.628. So I'm just going to include that in the first step. Okay, now let's see. The second step is telling us, well, really the third step. So now we have to make sure that it's approximately normal. So now we're going to take n times p hat, which is 1,000 times 0.372, which gives us 372. And then n times q hat, which is 1,000 times 0.628, which is 628. Okay, this is greater than or equal to 5. This is greater than or equal to 5. So because of that, it's approximately normal. Approximately normal. Okay, cool. So it's approximately normal, which means we can find the z-score, which will, and I'm going to condense those two as well. So I'm going to do z sub c because it's just looking at our chart that we already have. So if c is 0.95, I'll record that too. C equals 0.95. Okay, if we go to our standard normal table, okay, 95% is 1.96. Okay, and this helps us find E. So I'm kind of gonna do these in one. P hat Q hat over N. So just a plug and chug, 1.96 times the square root of 0.372 times 0.628 over 1,000. Okay, and it's the square root of all that. So this comes out to be approximately, there's, let's see, 3 decimal places. So we need 3 decimal places when we're rounding, and I got 0.030. Okay, and then step 4, we will find the confidence interval and then interpret it. So p hat minus e, p hat plus e, and then plug away. So 0.372 minus 0.03 is less than p, is less than, I'll put it there, 0.372 plus 0.030. So we get 0.342, it's less than p, is less than 0.402. So with this, we can say, I wonder if I can type here. I thought I could. I can just start typing. Ooh, cute, but I don't want it that large. Okay. Okay. This might just help me a little bit. My wrist is starting to hurt from all the typing. Okay. With 95% confidence, you can say that the population proportion, which is just going to be P of US teens who own smartphones is, I guess I should separate those, is between 34.2% and 40.2%. Oh, I like that a lot better. Look at how nice that looks. So cute. Okay, perfect. Cool. So, on the next page, we are going to be finding, we're going to be doing kind of the exact same thing. Okay, and then after that, we're going to be finding the minimum sample size. So let's get to it. Come on, let's get to it. I know that we can do it. Okay, in a survey of 498 US adults of who the most dangerous drivers are, it shows that the most dangerous drivers were made up of the following: 71% teenagers, 25% of people over 65, and 4% had no opinion. So we're going to construct a 99% confidence interval for the population proportion of US adults that think teenagers are the more dangerous driver. So if we're just looking at teenagers, I do not need the 25% and the 4%, okay, because those don't specify to teenagers. So let's go through my steps. So my N, my sample size, is going to be the 498. And then I don't have X. They actually give me the population proportion already, because that's what the 71% is. So, and that's the sample proportion, not the population proportion. So it's the sample proportion of 0.71. which means Q hat is 1 minus 0.71 or 0.29. Okay, now let's see if we can approximate it normally. So N times P hat, which is 498 times 0.71, which is, let's see, 353.58. And then N times Q hat, which is 498 times 0.29, and that is 144.42. Okay, so these are both greater than or equal to 5. So that means it's approximately normal. Okay, so we can use z-scores when we're finding this confidence interval. That's what that's saying. So now step 3, let's find our z-score. So if our confidence interval is 99%, then our critical z-value, let's see what that is, 2.575. Okay, and then we're going to find the margin of error, which is z sub c, square root of p hat times q hat over n. So we get 2.575 times the square root of 0.71 times 0.29 divided by 498. Okay, and since I have 2 decimal places, I'm only going to round this to 2 decimal places, so I get approximately 0.05. Okay, and that's just because the original was 2 decimal places, so I'm just doing 2. Okay, now let's construct the confidence interval. Oh, I changed it to purple. Okay. So this is p hat, which is the sample proportion minus e, is less than the population proportion, because we're saying that we're pretty confident that the actual population proportion is in between these two values. 0.05 is less than P, which is less than 0.71 plus 0.05. So this should be 0.66. And this should be 0.76. Okay, now my typing skills. Okay, let's see. With, just make it a little smaller. With 99% confidence, you can say that the population proportion of U.S. adults that, oh, okay, that went all the way to the end, that, or who think that teenagers are the more dangerous drivers is between 66% and 76%. And that's it. Okay. So just like in one of our previous notes, for confidence, or for precision, I should say. So if you're trying to be a little bit more precise without changing your confidence interval, then you can always increase the sample size. So to do that for P, so we're solving for N, and N is P hat times Q hat times Z sub C over E squared. Okay, and this assumes you have values for P hat and Q hat. Okay. If not, if you don't, then it's going to be like a 50-50 shot. Okay, then assume that P hat equals 0.5 and Q hat equals 0.5. That's if they don't give it to you. Okay, so last example. I know these are long, guys. You guys are doing great. We're getting through it. So with this one, you are running a political campaign and wish to estimate with 95% confidence the population proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the population proportion. We're going to find the minimum sample size needed. Now there's two things here. When no preliminary estimate is available, and then when P hat is 0.31. Okay, so for our formula, so this is going to be for 1, so no preliminary estimate means that we're going to have a P hat of 0.5 and a Q hat of 0.5. Now the 3% is your margin of error, and we're turning that into a decimal. So we move the decimal place over twice to the left, and it becomes 0.03. Okay. Then also, what are we given here? Oh, C is 95%, 0.95. So that critical Z value should be 1.96. And you can look at that on your chart. Okay, now it's just a plug and chug. So N equals P hat Q hat C sub C over E. We're going to square that. So if we were to plug it in, we'd get 0.5 times 0.5 times 1.96 over 0.03 squared, which is approximately 1067.11. Now, it doesn't matter what the decimal point is after, we always round it up. So that's about 1068. So you need at least 1068 voters, I guess, for your sample size. Okay, where for option 2, we do have a p hat of 0.31. We have a q hat of 0.69. And then everything else is the same. So E is still 0.03. And the C is 0.95, so Z sub C equals 1.96. Okay, so now we're just going to plug it into our formula. So our formula is N equals P hat Q hat C sub C over E squared. So we get 0.31 times 0.69 times 1.96 over 0.03, and that has to be squared. Okay, if you were to plug that into your calculator, you'd get about 913.02. But again, you always round up. As long as there's a decimal point after it, you're always rounding up. So we would need at least 914 voters. So if we are comparing our results, we would find we have found that with no preliminary estimate, the minimum sample size would be larger than if you did have a preliminary estimate. And that'll happen every single time, okay, because this should always give you larger than anything else, because they're saying, well, it needs to be at least this, so they're going to kind of shoot higher than what they would assume. Okay, that's it for chapter 6, guys. We only have chapter 7. You're plugging away. Great job. Okay, if you have any questions, please let me know. And again, once you get the exam, just start recording your answers to these, and you'll do great. Okay, miss you all. Bye.